In the previous example, we used the fact that the principal logarithm of z is equal to this expression to find the harmonic conjugate of the real part, which was the logarithm of the absolute value of z. So knowing that this function is an analytic function, we know that this must be the harmonic conjugate of the real part. Okay, assume that we wanted to find the opposite, and this is what we are going to do now. The opposite is that given this function, the argument value of z, what would be the harmonic conjugate of this function? And in order to do this, we just multiply with I on both sides of this identity. And what we then get is that I multiplied with the principal logarithm of z is just equal to this, and multiplying I with I, we obtain -1. So then we obtain that this complex function, which also must be an analytic function because it's just multiplied with a constant, this function must have this real part, and this must be the imaginary part of this function. So if we just now we see that we have minus the argument value of z as the real part. We wanted to find the harmonic conjugate of this guy without this minus, so we just multiply with -1 on both sides, and then we obtain this. So what we are seeing here is that we have some analytic function multiplied with the constant -I, which gives a new analytic function, and therefore this function must have real part here, and the harmonic conjugate of this real part must be this guy. So this shows that the harmonic conjugate of the principal argument of z is minus the logarithm of absolute value of z. This we are going to use in the next example 6, where we have the following potential. We have seen this before. We have a constant a multiplied with this theta plus b. So a and b are real constants. We see that this theta is just, as we have observed before, is just equal to the principal argument of z. So we can replace this theta by this, and considering this function, which must be an analytic an harmonic function, we can of course find the harmonic conjugate of this. And going back now, we see that the harmonic conjugate, we found that the harmonic conjugate of the principal argument is just equal to minus the logarithm of the absolute value of z. So therefore, when we know that we have to multiply with this constant a to the principal argument, we also must multiply with a for the harmonic conjugate of this potential. So therefore we can conclude that the imaginary part of the complex potential is just equal to this function. So summing up, we find that the complex potential, which we always call capital F, is equal to phi plus I psi, and we insert these two expressions and obtain this. Now we can collect all terms connected to or associated with this constant a, and doing this we we see that this part is just equal to, going back and see what we did above, this is exactly the same as we have on the right hand side here, which is equal to this complex function. So therefore I obtain this, and we know have that the complex potential is just minus a times I multiplied with the principal logarithm of z plus some arbitrary constant b, and we can also add any imaginary constant to this. So this b does not need to be a real number. So here is the complex potential associated with this potential phi.